Welcome back. In this unit, we will talk about CPU scheduling. The definition of scheduling is as the following. We want to schedule a set of jobs. Each job I has two given parameters. AI, the arrival time, the time that job I arrives. Ri, the runtime, the time it takes for the job I to complete. For each job I, we define response time, time between the job's arrival and when the job starts to run. That is, the time that job I starts to run minus AI. Turnaround time, the time between the job's arrival and when the job finishes running, that is, the time that the job completes minus AI. Our goal is to minimize average response time or average turnaround time. In the next few slides, we will discuss two basic schedulers and their preemptive variants. First come first serve runs jobs in arrival time order. It is simple to implement and avoids starvation. The drawback of it is that it is not efficient. Shortest job first runs jobs in runtime order. It minimizes average turnaround time, but long jobs may starve. The preemptive variant of first come first serve is round robin, and the preemptive variant of shortest job first is shortest remaining time first. Let's look at this example here. We want to schedule jobs J1, J2, J3, and J4. Let's first use first come first serve scheduler. At time t equals 0, J1, J2, and J3 have arrived. We can pick either J1, J2, and J3. Let's pick J1 here. J1 runs for 5 seconds from time 0 to 5. Next, at time t equals 0, J2, J3, and J4 have arrived. Because J2 and J3 arrived before J4, so let's pick either J2 and J3 here. We pick J2. J2 runs for 8 seconds from time t equals 5 to time t equals 13. Now we are at time 13 and J3 and J4 have arrived. J3 arrived before J4. So let's run J3 here for 3 seconds from 13 to 16. J4 is the only remaining job now, so we run J4 for 2 seconds from 16 to 18. The average turnaround time is 1 over the number of jobs, 1 over 4, times the turnaround time of J1 is 5 minus 0. The turnaround time of J2 is 13 minus 0. The turnaround time of J3 is 16 minus 0. And the turnaround time of J4 is 18 minus 5. 11.75. Now we will use the shortest job first scheduler. At time t equals 0, J1, J2, and J3 have arrived. J3 has the shortest runtime of 3, so we run J3 for 3 seconds. Next, at time t equals 3, J1 and J2 have arrived, and J1 has the shortest runtime of 5, so we run J1 for 5 seconds from 3 to 8. Now at time t equals 8, J2 and J4 have arrived, and J4 has the shortest runtime of 2, so we run J4 for 2 seconds from 8 to 10. Now the only job remaining is J2, so we run J2 for 8 seconds from time t equals 10 to 18. The average turnaround time is 1/4 times. J3 completes at t equals 3 and arrives at t equals 0, so 3 minus 0. J1 completes at time 8 and arrives at time 0, so 8 minus 0. J4 completes at time 10 and arrives at time 5, 10 minus 5. J2 completes at time 18 and arrives at time 0, 18 minus 0, 8.5. Now let's schedule the jobs with a quantum of 2 seconds. We first use the round-robin scheduler. Let's put the arrival queue here. At time t equals 0, J1, J2, and J3 arrived. The head of queue is J1, so we run J1 for 2 seconds, and the runtime of J1 is now 3. And we insert J1 to the back of the queue. The head of queue is J2, so we run J2 for 2 seconds, and the runtime of J2 becomes 6. And we insert J2 to the back of the queue. The head of the arrival queue is J3. We run J3 for 2 seconds, and the runtime of J3 becomes 1. Notice that J3 runs from time t equals 4 to time t equals 6, and at time t equals 5, J4 have arrived. And we insert J3 to the back of the queue after it completes. The head of queue is now J1, so we run J1 for 2 seconds, and the runtime of J1 becomes 1. And we insert J1 to the back of the queue. The head of queue is J2, so we run J2 for 2 seconds, and the runtime of J2 becomes 4. And we insert J2 to the back of the queue. Now the head of queue is J4, so we run J4 for 2 seconds, and J4 completes. We don't need to insert J4 to the back of the queue. The head of queue is J3, and the runtime of J3 is 1, which is less than the quantum of 2 seconds, so we run J3 for 1 second, and J3 completes. The head of queue is J1, and the runtime of J1 is 1, so we run J1 for 1 second, and J1 completes. Now the only job remaining is J2, and the runtime of J2 is 4 seconds. So we run J2 for 4 seconds. The average turnaround time is 1/4. J1 completes at time 14 and arrives at time 0, so 14 minus 0. J2 completes at time 18 and arrives at time 0, 18 minus 0. J3 completes at time 13 and arrives at time 0, 13 minus 0. J4 completes at time 12 and arrives at time 5, 12 minus 5, 13. Next, we will use shortest remaining time first scheduler. At time t equals 0, J3 has the shortest remaining runtime of 3, so we run J3 for 2 seconds. And the remaining runtime of J3 becomes 1. Now, at time t equals 2, J1, J2, and J3 have arrived, and J3 has the shortest remaining time of 1, so we run J3 for 1 second and J3 completes. Now at time t equals 3, J1 and J2 have arrived, and J1 has the shortest remaining time of 5, so we run J1 for 2 seconds. And the remaining runtime of J1 is now 3. Now at time t equals 5, J1, J2, and J4 have arrived, and J4 has the shortest remaining runtime of 2 seconds, so we run J4 for 2 seconds and J4 completes. Now at time t equals 7, J1 and J2 have arrived, and J1 has the shortest remaining runtime of 3, so we run J1 for 2 seconds, and the remaining runtime of J1 becomes 1. Now at time t equals 9, both J1 and J2 have arrived, and J1 has the shortest remaining runtime of 1 second, so we run J1 for 1 second and J1 completes. Now at time t equals 10, the only remaining job is J2, and its runtime is 8, so we run J2 for 8 seconds. And J2 completes at time 18. The average turnaround time is 1/4 times. J1 completes at time 10 and arrives at time 0, 10 minus 0. J2 completes at time 18 and arrives at time 0, 18 minus 0. J3 completes at time 3 and arrives at time 0, 3 minus 0. J4 completes at time 7 and arrives at time 5, 7 minus 5, 8.25. We have discussed the definition of scheduling, what goals it achieves, and 2 basic schedulers and their preemptive variants so far. In CPU scheduling, the jobs to be scheduled are the threads. CPU scheduling differs from the simple scheduling model. The runtimes of each thread is unknown. Threads are sometimes not runnable. That is, they are blocked and put on the wait channel. Threads may have different priorities. The objective of the CPU scheduler is to achieve a balance between responsiveness, ensure that threads get to run regularly, fairness, and efficiency. Let's first look at how to achieve responsiveness. Let's consider this question: what is good responsiveness? We consider two threads of the same process. Thread 1 does simple computation and the result is only needed after 1 hour. Thread 2 runs an interactive console. What are their differences? For thread 2, we want to see the character displayed on the screen immediately after we type it. So thread 2 requires good responsiveness. For thread 1, because we don't need the computation result until 1 hour later, thread 1 doesn't need good responsiveness as long as it gets to complete in 1 hour. We call threads like thread 1 as non-interactive threads and the threads like thread 2 as interactive threads. So in general, we want interactive threads get good responsiveness and the non-interactive threads get to run as much as possible. To achieve this objective, we assign higher priority to interactive threads and lower priority to non-interactive threads such that the interactive threads have precedence over non-interactive threads. So how to determine which threads are interactive and which aren't? What is the characteristic of interactive threads? Let's look back at the interactive console example. The console is frequently blocked to wait for keyboard input response from the user for prompts, so interactive threads are frequently blocked. We want to group threads that require the same level of responsiveness together, and we always want to start with the threads that require the highest level of responsiveness. To do this, we maintain n round-robin queues Q1 to Qn. Qn stores most interactive threads and Q1 stores least interactive threads. Threads on Q1 are not frequently blocked, so we want threads on Q1 to progress as much as possible before it is preempted, so it requires a large quantum. Threads on Qn are frequently blocked, so it only needs a small quantum. So in general, we assign n quanta Q1 to Qn, where Q1 is greater than or equal to Q2. And Q2 is greater than or equal to Q3, and so on. All threads are initially assumed to be very interactive, so we put them on Qn. Scheduler always chooses thread from Qn unless it is empty. If Qn is empty, then we choose a thread from Qn-1. Unless it is empty. And so on. If a running thread from Qi uses its inquiry quantum and gets preempted, we demote it to Qi-1. Let's look at this diagram here. All threads are initially put on Q3, and if a running thread from Q3 uses its entire quantum and gets preempted, we demote it to Q2. If a running thread from Q2 uses its entire quantum and gets preempted, we demote it to Q1. If a thread is blocked and put on the wait channel, we put it into Qn again when it wakes up. So when a thread that is blocked wakes up, it is put on the Q3 again. To prevent starvation, we periodically move all threads to Qn. This mechanism here is called multi-level feedback queues. Next, let's look at how to solve the fairness goal. Our goal is to ensure that each job gets a fair share of the CPU. In other words, we want jobs with longer runtime to run less frequently and jobs with shorter runtime to run more frequently. Our solution is to assign a weight to each thread. We define the virtual runtime of a thread proportional to its actual runtime. This coefficient alpha here is a function of the weight. The weight of the thread over the sum of all weights. Scheduler picks the job with the shortest virtual runtime to run. As a result, if the weight of a thread increases, then its virtual runtime increases since its virtual runtime is proportional to its weight. Because the scheduler always picks the job with the shortest virtual runtime and the virtual runtime of the thread is increased, so the thread gets less frequent to run. This mechanism here is called Linux Completely Fair Scheduler. So far, we have considered the CPU scheduling for processors with only one core. Let's consider when we have a processor that has more than one core. Multi-core processor scheduling. There are two mechanisms that can be used in multi-core processor scheduling. Per-core ready queues. That is, each core has its own separate ready queue, shared ready queue. All cores share the same ready queue. We will evaluate these two mechanisms from four aspects: contention, scalability, CPU cache affinity, and load imbalance. In terms of contention, the shared ready queue design needs a mutex to protect the ready queue. Every time the scheduler adds or removes a job from the ready queue, it needs to acquire the lock or the mutex first. And as the number of cores increases, the contention also increases. For per-core ready queue design, contention is not an issue since each core has its own separate ready queue, so we don't need to protect the ready queue at all. In terms of scalability, it is very simple for the per-core ready queue design to add a new core. We simply need to add a new ready queue that is associated with the new core. For the shared ready queue design, we need to change the ready queue add and remove routines to support the newly added core, which is complicated. In terms of CPU cache affinity, let's first understand what is CPU cache affinity. Threads may have affinity to a certain core as most of the data it accesses are loaded in that core's local caches to make use of the cached data. For the per-core ready queue design, we can always assign a thread to a certain core which has local caches that contains the data that the thread assigns to. This can be done easily by placing the thread on that core's ready queue. For the shared ready queue design, it is hard to achieve CPU cache affinity. Because all threads are put on the same shared ready queue, threads can be run on any core. It is hard to keep a thread on a certain core. Some cores are lightly loaded while others are heavily loaded. Threads on lightly loaded core get more CPU time than threads on heavily loaded cores. For per-core ready queue design, let's consider an extreme case. We have a processor that has two cores, core 1 and core 2. Core 1 is completely idle, meaning that there is no job running in core 1. Core 2 is extremely heavily loaded. Because we want to achieve maximum throughput, so we need to migrate some of the threads that are on the ready queue of core 2 to the ready queue of core 1 so that core 1 is not idle. This thread migration mechanism is very difficult to implement. For the shared ready queue, load imbalance is not an issue, as what we just discussed earlier in the CPU cache affinity. Because all threads are put on the same shared ready queue, threads can be run on any core, so all cores are almost equally loaded. By the end of this video, you are expected to know the definitions of response time and turnaround time, how to run first come first served scheduler and the shortest job first scheduler, how to run round robin scheduler, and the shortest remaining job first scheduler. What is multi-level feedback queues and what it achieves? What is Linux completely fair scheduler and what it achieves? Compare per core ready queue and shared ready queue in terms of contention, scalability, CPU cache affinity, and load imbalance.